Hey everybody, welcome back to Complex Analysis. And we're going to be talking about functions of z, where z is the complex number x plus iy. And we make the remark here that if w is some function of z, in other words, some function of f evaluated at x plus iy, we might suspect that w, or f of z, is of the form u, where u is a function of x, plus iv, where v is a function of y, for some functions u and v, where u of x is the real part of w, and v of y is the imaginary part of w. In other words, we might imagine that if w is a function of z, then the real part of w is a function strictly of x, and the imaginary part of w is a function strictly of y. But that's not the way it usually works. And to see that, let's just consider an example. F of z equals z squared. So z is x plus iy squared. And when we square something, we get the first thing squared, plus the second thing squared, plus 2 times the first times the second. So that's going to be 2i xy. If we square the I, we get negative 1, so this is just going to be negative y squared. And look what we have here. This is the real part of w. And it's a function both of x and y. And here's the imaginary part of w. And it too is a function both of x and y. So in terms of u and v, we have this function f of z that we call w. W is a function of z, in this case z squared. And the real part of w turns out to be some function u of both x and y. And the imaginary part of w turns out to be some function v of both x and y. And in general, this is going to be the point. So let me just say that explicitly. So the point of all of this is, if we have w, which is a function of z, x plus iy, and we have real part of w plus I times imaginary part of w, it's generally going to be the case that u, the real part of w, is going to be a function both of x and y, and v, the imaginary part of w, will also be a function of x and y. And so what we're going to do now is take a second look at some familiar complex valued functions. In particular, we're going to look at the exponential function and the natural logarithm. So consider this. For a real number x is a real number, Consider the real valued function, w equals f of x, which equals e to the x, where x is a real number. The domain of f of x is the entire set of real numbers. Now, associated with this function, w equals f of x, we have f inverse of w, the natural logarithm of w, where the domain of this function, f inverse or natural log of w, is the set of positive real numbers. Now again, consider the function f, which has as its domain the entire set of real numbers, and its image, the set of positive real numbers, given by w equals f of x, which equals e to the x. This function is one-to-one and onto. So for every positive real number here, there's a real number over here that we can plug into the function of x and get this positive real number. Also, it's one-to-one, which means that no two real numbers here are mapped to the same real number here. And now let's consider f inverse from the set of positive real numbers to the entire set of real numbers, given by x equals f inverse of w, or the natural log of w. F inverse, the natural log of w, is also one-to-one and onto. So no two distinct elements here get mapped to the same element here by the natural logarithm function. And for every element, every real number, there's a positive real number over here that the natural log of x, or the natural log of w rather, maps to this real number over here. And I guess one final observation, and this may seem like a very peculiar thing for me to say, but since these are functions, we can't take a value of x and plug it in here and get 2, 3, 4, 10 different values. We plug one value of x in here and we get one distinct value of f of x. And similarly here, we can't plug a value in here. We can't plug a single value of w in here and get more than one value over here. That's not the way a function works. So we plug one value of w into the function and we get one value out. And I say that because things are about to change. Okay, we extend the definitions of the exponential and natural logarithm functions. We extend the domains to include the complex numbers. So first of all, the exponential function. Let z equal x plus iy be any complex number at all. Then f of z, which equals e to the z, we say that's e to the x plus iy, which we can rewrite as e to the x times e to the iy. And e to the x is essentially r, the modulus of the complex number. And e to the iy essentially is cosine plus I sine of y. But this is what f evaluated at z equals e to the z turns out to be. R times e to the iy, where r is the modulus of z. Now let's look at the natural log function that we extend to the complex numbers. And we have a complex number in polar form or exponential form, w equals r e to the iy, where r is the modulus of the complex number. And notice, since r is the modulus and it's e to the x, where x is a real number, r is never 0. So the domain for f inverse of w, the natural log function, consists of all complex numbers except 0. So we've extended the definition in the domain of the natural log function to include the entire set of complex numbers except for 0. Regardless of whether we're looking at the natural log function as a real valued function or a complex valued function, if we plug 0 into this thing, things go horribly wrong and our entire solar system gets sucked into a black hole and we're never heard from again. So all complex numbers are fair game to plug into the natural log function, except 0. And we apply the properties of natural logarithm. Natural log of r times e to the iy is natural log of r times natural log of e to the iy. Remember, natural log of a product is the sum of the two natural logs. So that's why this happens. And that gives us natural log of r. And natural log and e are inverses. So natural log of e to the iy, that's just going to be iy. So plug in the complex number w equals r e to the iy into the natural log function, and we get natural log of r plus iy. But there's a catch. And by the way, I have labeled this as being equation 1 for a reason. I'm going to go back to this. So we take w equals r e to the iy and plug it into the natural log function. We get natural log of r plus iy, equation 1. Yep, we're going to have to revisit this because there is a catch. So we came up with equation 1 and I said there's a catch. Okay. Here's where the trouble comes in. We have e to the iy, which is exactly the same thing as cosine of y plus I sine of y. But isn't this equal to cosine of y plus I sine of y? Oh, what am I going to do here? Plus 2k pi plus 2k pi for any whole number value of k. We take an angle, add a multiple of 2 pi to that angle and plug it into cosine. No difference. The cosine of y and the cosine of y plus a whole number multiple of 2 pi, exactly the same. Same thing with sine. The sine of y and the sine of y plus a whole number multiple of 2 pi, no difference. So this thing and this thing are exactly the same. Now, here's what it means for our exponential function. What it means is that these two things are exactly the same for for any whole number multiple of pi. In other words, as long as k is an integer, these two things are exactly the same. And that's going to have a bearing on what equation 1 is. Well, so far so good. We haven't done anything different than what we did before. But now we're going to incorporate this observation in what we have down here. Specifically, natural log of e to the iy. Same exact thing as natural log of e to the I times y plus 2k pi and let's see, that's going to equal natural log of r plus I times, natural log and e undo each other, so this is just going to be I, y plus 2k pi for all whole number values of k. And let me generalize that. Here's our complex number in exponential or polar value or polar form. And we're going to get natural log of r plus I times theta plus 2k pi. And let's see. This will work for any value of k that's an integer. So, essentially, the natural log of w is a function with infinitely many branches. And remember, we talked about branches a little bit before in the previous lecture. But the natural logarithm function, as a complex valued function, has infinitely many branches. And we're going to expound on that in just a second. So again, this function has infinitely many branches. One branch for each whole number value of k. The principal branch is going to correspond to k equals 0. So the principal branch will be natural log of r plus I theta, where theta is between 0 and 2 pi and includes 0. Now, for any other whole number value of k, we get a different branch. We'll talk more about that later. Let's get back to what we were talking about earlier. What we really want to do or focus on at this point is looking at the exponential function, f of z equals e to the z, and the logarithm function, f inverse of w is the logarithm of w, as being functions that have a real part and an imaginary part. And both the real and imaginary parts are functions of the real and imaginary parts of the original variable z. For example, f of z is equal to, well, we called that w, didn't we? W is equal to f of z, and that's equal to e to the z, e to the x plus iy. And we can write that as e to the x times e to the iy. And that turns out to be e to the x times cosine of y plus I sine of y. And we can distribute the e to the x in the parentheses. Like I said, we can distribute the e to the x into the parentheses. I think maybe I need a script to follow. So this is our u of x and y. And this much is our v of x and y. Now we also want to do the same thing for the natural log function. Before I do any more, I'll just let you look at that for a second. Okay. do here. And now in terms of the rectangular coordinates, where W equals U plus IV, this is our function X of UV, and this is our function Y of UV. And we might wonder about that, but remember where the modulus comes from. R is U squared plus B squared. And theta is the arctangent of V over U. And depending on what quadrant theta is in, we might add a plus pi. But essentially, theta is a function of U and V. And the real part, natural log of R, is a function of U and V also. Just one more comment before we do some examples. Our author calls these functions transformations, perhaps because of the way F transforms the graph of Z and how F inverse transforms the graph of W. So when our author talks about transformations, he's just talking about these functions, but perhaps with a special interest in what the function, or how the function takes a particular region in the XY plane and transforms it into a region of another shape into the UV plane. Now, I think we want to do some examples. Okay, let's take this function and write it as U, some function of X and Y, which is the real part of this function, plus I times v, the imaginary part of this function, where v is also a function of x and y. So here's what I think I'll do. I'll just write out what the function is and write it in terms of x and y. And this is a binomial raised to the fourth power. So if we don't know what this is supposed to be, we can just use the binomial theorem. So let's see, 4 choose I, x to the 4 minus I, y to the I. Okay, and we have I equals 0. So that's 4 choose 0, x to the 4 minus 0, y to the 0, plus 4 choose 1, x to the 4 minus 1. I is 1 here. Y to the 1. Okay, now I is 2. 4 choose 2, x to the 4 minus 2, y to the 2. Now I becomes 3. 4 choose 3, x to the 4 minus 3. Whoops. Oh my goodness, I should be shot. We're not computing x plus y to the fourth. We're computing x plus iy to the fourth. I should be shot, but please don't shoot me. Okay, that's much better. 4 choose 4, x to the 4 minus 4, times iy to the fourth. 4 choose 0 is 1, x to the fourth. Iy to the 0 is just 1. 4 choose 1 is 4. X cubed iy to the first. 4 choose 2 is 6, I hope. X squared iy squared. 4 choose 3 is 4. X to the first, iy to the third, and 4 choose 4 is 1. X to the 0 is 1. And iy to the fourth. Okay. So we have x to the fourth, and we have I times 4x cubed y. So I'll say 4i x cubed y. Nah, I'll do it this way. I 4x cubed y. We have I squared times y squared. I squared is negative 1. So negative 1 times 6 will give us negative 6 times x squared times y squared. Okay, now we have I cubed times y cubed. I cubed is negative I times 4x y cubed And then here we have I to the fourth times y to the fourth. I to the fourth is just 1. So this boils down to y to the fourth. Now, I think I want to group my reals together because I want to write this in the form of u of xy plus iv of xy. So our real terms are x to the fourth minus 6x squared y squared plus y to the fourth. So those are my real terms. And my imaginary terms, I have I 4x cubed y and minus I 4xy cubed. So let's put plus y and 4x cubed y. Whoops, whoops, whoops. And we also have I times minus 4xy cubed. So I think that's pretty well got it. X to the fourth minus 6x squared y plus y to the fourth plus I 4x cubed y minus 4xy cubed. And that's exactly what we wanted. Here is our real part, u of xy. And here's our imaginary part, v of xy. Bravo. Another example. Write f of z in the form of uxy plus ivxy. Given that f of z is equal to z conjugate times the real part of z plus z squared plus the imaginary part of z. Okay, let's just write it out and see what happens. So z conjugate, real part of z, plus z squared, plus imaginary part of z, z conjugate. Now z is written as x plus iy, so z conjugate will be x minus iy. Times the real part of z. Okay, here's z and we want the real part of that. And then we have z squared, where z is x plus iy. And then we have the imaginary part of z. Real part of x plus iy, that's just x. So we have x minus iy times x. And then we need to do this thing. We need to square this out. And when we square a binomial, we get the first thing squared. And we get the second thing squared. Now, if we square I, we get negative 1. So this is going to be negative y squared And then we get 2 times the first times the second. So that's 2 times IXY. How do I want to write this? Okay. And the imaginary part of this is just y. Okay, oops, never mind. I haven't multiplied this out yet. So we get x squared minus IXY plus x squared plus I2XY minus y squared plus y. Okay, now I can just regroup. And I'm going to get all my reals together. So I have x squared plus x squared is 2x squared plus y minus y squared. So 2x squared plus y minus y squared. Those are all of my reals, I hope. I think so. And now we combine our imaginary terms. Negative IXY plus 2IXY is just IXY. Yeah, that's it. Okay. So here is u of xy. And this is our v of xy. And we'll encapsulate this answer because that was exactly what we wanted to do. Here's an interesting example that we're given f of z in the form of u of xy plus I times v of xy. And here they want us to write it in terms of z. Well, I think what we should do is refer to some identities that express x as a function of z, and they express y as a function of z. I'm pretty sure we've seen them, but we probably haven't done a lot with them since we first saw them. So let's remind ourselves of what these identities are. Now, let me just check and make sure this is right. Z plus Z conjugate over 2. So that's going to be x plus IY plus x minus IY over 2. And the IY's cancel out, so we have 2x over 2, or x. So this one works. Z plus Z conjugate over 2 equals x, okay. And let's make sure the other one does. I'm pretty sure I remember this correctly, but you know how I am. Sometimes I do, sometimes I don't. Z minus Z conjugate over 2i. I usually forget the I here. So let's see, x plus IY minus x plus IY. Whoops, z conjugate minus x minus iy. They are much, much better. Over 2i. And we have x minus x is 0. Iy minus a negative iy is 2iy, or I times 2y, over 2i. And we cancel 2y out of top and bottom, and we get y rather. So yes, y indeed does equal this mess. So these are going to be the two identities that we use. I just wanted to check them and make sure that I had them written correctly. And also to remind ourselves of where the identities came from in the first place. So here's what we're going to do. We're going to plug this in for x. We're going to plug this in for y in this equation. F of z, 4x squared, plus I times 4y squared. And so that's going to be 4 times this mess squared, z plus z conjugate over 2 squared, plus I times 4 y squared, and that's z minus z conjugate over 2i quantity squared. And here we get the first thing squared, z squared, plus the second thing squared, plus 2 times the first times the second, 2z conjugate. And we have I times 4. And on the bottom we have 2i squared. I squared is negative 1. 2 squared is 4. So negative 4 on the bottom. And we square this, so we have the first thing squared plus the second thing squared and then plus the first times the second, plus 2 times the first times the second. So 2 times z, negative z conjugate, is negative 2z, z conjugate. Okay, I think that's what we've got. So we have z squared plus 2z, z conjugate, plus z conjugate squared. And let's see, 4 and a negative 4, so we got minus I, times z squared minus 2z, z conjugate, plus z conjugate squared. And maybe we can tidy this up just a little bit. Let's see, as far as z squared goes, we have 1 times z squared minus I times z squared. So I'll say 1 minus I, z squared. So let's see, I've accounted for these guys. Now let's see, I have 2z, z conjugate, and I have minus I times minus 2z, z conjugate. So let's see, 2 and 2i times z conjugate. So 2 plus 2i times z conjugate, I hope, Yeah, that's right. And then z conjugate squared, I have 1 times z conjugate squared and minus I times z conjugate squared. So that would be 1 minus I z conjugate squared. Okay. I think I will quit while I'm ahead here. And I will say that that is my function of z. By the way, maybe the value of this exercise is if we have f of z given in terms of u of xy and v of xy, and we want to write it in terms of z, this is how we do it. We take the identities that give x in terms of z and y in terms of z and plug those in for x and y. How about one more example? In keeping with our u plus iv theme, writing a function in terms of real part and I times imaginary part, express f of z in polar form, where f is the function 2z squared minus 3z plus 5. So I guess since I'm going to write it in polar form, the first thing to do is just take my z and write it in polar form. So z equals r e to the I theta, which is r cosine of theta plus I sine of theta. And everything's straightforward here except I'm going to need a z squared, so let me compute that. And remember, if we take something in polar form and raise it to the nth power, we get the modulus raised to the nth power. And the angles are multiplied by n. So this is what happens when we square z. Okay, now I guess I just plug all of this in. F of z is 2z squared minus 3z plus 5. And I'll plug in this mess for z squared, so I'll get 2r squared cosine 2 theta plus I sine of 2 theta. And then I have minus 3z. So z is what? R cosine theta plus I sine theta. Two z squared minus 3z plus 5. Okay. Now I have it in terms of r and theta. I just need to take what I have here and get my real part and my imaginary part. So let's see. You know what? I think I'll distribute this junk inside the parentheses first. So let's see. 2r squared cosine 2 theta plus I 2r squared sine 2 theta and then I'll do the same thing over here, minus 3r cosine of theta minus 3r I sine of theta plus 5. Okay, now I can clearly write this in terms of a real and imaginary part. So I have 2r squared cosine of 2 theta. That's definitely real. And I have minus 3r cosine of theta. That's definitely real. And 5, that's definitely real. So I think almost certainly this is going to be my u of r theta. And now I'm going to have I plus I 2r squared sine 2 theta and minus I 3r sine theta. So let's see, I times minus 3 r sine theta. And that exhausts all my imaginary parts, doesn't it? So I think, unless I've done something that I should be extremely ashamed of, that this is v of r theta. Okay, looks good. I don't see anything for which I should be ashamed. I will send out some homework exercises of this type right after I post this video.